Hey everyone, welcome to our next video. We're continuing 6.5 in this video. So this is like the part 2 to 6.5. So I'm just going to say 6.5 continued. So in this one, I want to start off talking about what if it's not just x inside of those parentheses. Like what if there's something else in there? So here's what I'm talking about here. So I'll say example 1. And there's a bunch going on in this section. So I'll still just say solve for all values of x. So remember from the last video, if it says for all values, then you're going to have to do like the plus something k thing. If it just gives you some kind of interval, then you'll only give answers within that interval. So that's something that we have to watch out for in the directions. So for our first one, I want to do sine 2x equals square root 2 over 2. The first thing that I like to do for these is I like to let the inside of the parentheses equal something else. So I'll say let 2x equal, let's just do z. So then I have sine z equals square root 2 over 2. Now you can treat it just like a problem from the beginning of 6.5. So it's just a basic equation. So let's think, we want to remember, I'm going to write my table and all that over here. I always reference back to that, so I'm going to go ahead and write it out. I've got my unit circle here with just the quadrantal angles because of all those zeros and negative ones and everything, just to kind of have that to look at. And then I'll also write out my table. And I usually just do sine and cosine on it, and then if I need other angles, then, like other ones like tangent, then I'll put them on after. Okay. So if I look at this, right now I'm not worried about the 2x, like that's gone for now. We'll come back to that later. Right now I'm just worried about z being in here. So I need to find the angles that z would need to be so that sine equals square root 2 over 2. So I know my reference here would be 45 degrees, and sine is going to be positive in quadrants 1 and 2. So I'm looking for references of 45 degrees in quadrants 1 and 2. Quadrant 1 is just going to be itself 45 degrees. So I have z equals 45 degrees plus 360k. And then I have z equals 135 degrees for quadrant 2. And we'll still have our 360k. Now I'll replace back in this 2x instead of z. So I'll have 2x equals 45 degrees plus 360k, and 2x equals 135 degrees plus 360k. I need to solve for just x, so I'll divide both sides by that 2. So for my final answers here, I get x equals 22.5 degrees plus 180 degrees k, and I have x equals 67.5 degrees plus 180 degrees k. In radians, just to show you that for a moment, this would have been pi over 4, this would have been 2 pi, this would have been 3 pi over 4, this would have been 2 pi. And so then if I divided those by 2, I would have gotten pi over 8 plus pi k, and 3 pi over 8 plus pi k would be the answers in radians. Now again, like I said in the last video, I really don't mind if you choose to leave your answers in radians or degrees. I'm okay with either one. Whatever you like, that's what you should do. Whatever is easier for you. Something I want to say for this one is a lot of times when students see these, they see that 2x and it can make you almost think to use one of the identities. So of course on this test you're going to have the identity sheet. So when you're looking at the identity sheet, there is an identity. It's the double angle identity for sine 2x. There are going to be times where maybe we use an identity to help simplify an equation so that we can, work with it. This is not one of those cases where that would help. So the reason that it wouldn't help us is for instance, if I were to use that identity, what it would give me is 2 sine x cosine x equals square root 2 over 2. Okay, having multiple trig functions like that does not get us any closer to like a simple equation. Doing this, right, replacing the 2x with something that does. So you have to be careful about that. I'll tell you that usually, with me on my test, I will usually write something along the lines of use identities somewhere in a question where you need identities. So if I don't say anything about identities, you probably won't be using them. I can't say that 100%, of course, but that's kind of the usual for me. So part B, we'll do another example of this. So we're going to solve for x where x is between 0 and 1,000 degrees for this one. So this one, you're only going to give me answers within that interval. So we're not going to have the k at the end for our answer. So this one, we're going to do cosine x over 2 equals positive 1/2. So when I see something like this, when I have only one trig function, the only thing that's weird about it is that there's something else going on in the parentheses. I like to just let my parentheses equal something else. I usually just choose z. Here, let me bring my table and stuff down because I'm gonna need that. We always need that. That's why it's in like the second section that we ever did. So now I have cosine z equals 1/2. So my reference, cosine is 1/2 at 60 degrees. My reference is 60, and cosine is positive, since it's a positive 1/2, in quadrants 1 and 4. So I'm looking for the quadrant 1 answer is just going to still be 60, so I'll have z equals 60 degrees plus 360 degrees k. And then my quadrant 4 answer would be 360 minus 60, so that's going to be 300 plus 360k. Now I'm going to put back in my x over 2, so I have x over 2 equals 60 degrees plus 360 degrees k, and x over 2 equals 300 degrees plus 360 degrees k. Now you may be wondering, why do we still have this plus 360k when it's asking for an interval? Don't we not need the k anymore? Sort of. When we multiply in this 2, right? Because to get rid of that division, I got to multiply it on both sides. I'm now going to have x equals 60 times 2 is 120 plus 360 times 2 is 720. And I also have x equals 300 times 2 is 600 plus 720k. So what happens is whenever you multiply or divide or something like this to get your x value, you have to still consider the k right here because we may be able to add or subtract that value to get a new answer. So I'm only looking for answers between 0 and 1,000. 120 is between 0 and 1,000. 600 is between 0 and 1,000. And you also need to see if maybe adding 720 would give you another answer. So if I do 120 plus 720, that'll give me 840. So that's another answer. Now 600 plus 720, that does not give me a valid answer. So these are going to be my 3 answers within the interval 0 to 1,000. Let's do another one. So this is a good time that if you are trying these, on your own, you should pause and maybe try this one on your own. So I'm going to say solve for x in the interval 0 to 2 pi. So I only want between 0 and 2 pi. I don't want anything outside of that. And we're going to do 2 sine x plus pi over 6 plus 1 equals 0. So you should maybe pause the video and try that one on your own. I'm going to go ahead and bring this down first. You should go ahead and try it before you watch me solve it. That way if you start getting stuck, you know like what's tripping you up. So just like before, I'm going to take this and I'm just going to let it be like z or something. I'm going to say z equals x plus pi over 6. So I'll replace that back in later. I have 2 sine z plus 1 equals 0. If this was a problem like in the regular equations, we would solve this for sine, get it by itself. So I have negative 1 over 2. So I subtracted over that 1 and then divided by 2. My reference here is going to be 30 degrees. And I'm looking at a negative value here. So this negative means I need to look wherever sine would be negative, which is going to be 3 and 4. So I'm looking for the angles that have references of 30 in quadrants 3 and 4. Because I'm dealing in radians, because this is in radians and this is also in radians, I'm going to work with this in radians as well. So I'm going to change that from 30 to pi over 6. So this would be pi or 6 pi over 6. So the quadrant 3 answer would be 7 pi over 6 plus 2 pi k. I still do the k just for a moment, just in case if we added it, if we could get another answer, I got to consider that. And then I have z equals quadrant 4. This would be 2 pi or 12 pi over 6. So if I subtract pi over 6, that'll give me 11 pi over 6 and plus 2 pi k. Now I'll replace that x plus pi over 6 back in. To solve this, I can subtract pi over 6 from both sides. Seven pi over 6 minus pi over 6 is 6 pi over 6. Plus, I still have 2 pi k there. That didn't get changed at all. 11 pi over 6 minus pi over 6 would be 10 pi over 6. And I still have my 2 pi k. So for my answers within 0 to 2 pi, I have x equals 6 pi over 6 is just pi. 10 pi over 6 is 5 pi over 3, simplified. Now the thing about equations is remember that you can always plug your values back in to check them. I feel like sometimes people forget that in trig, like in algebra, anytime you have like an x equals, you can always plug it back in. Well, you can do that. Oh, sorry, I yawned. You can do that here as well. Alrighty, and I have one more of this kind of type for us that I want to do, and then we'll go on to the next subsection. This one I'll say, oh, let me make a little note here. If this problem, the one we just did, if it had said for all values, we would have just boxed it in like right here. We still could have simplified first, but we would have just left it with the k. Same thing for this one up here, part B. If it had said for all values of x, we would have just boxed in. Oh, I didn't mean to erase. We would have just boxed in right here. We wouldn't have had to do that last step of finding all the values in the interval. So let's just do one more. I want to do one of the reciprocal ones. So secant, this one is x divided by 3 equals 2, where let's do for all values for this one. All values of x. So just like before, I think you should pause first and just kind of try it on your own. But this, I'm going to let be z equals x over 3 just to get rid of that. Well, I got to put it in my other color. I like to stay consistent. All right, so also, actually, let me just write it like this first, and then we'll talk about that. I don't want to get ahead of myself. So I have secant z equals 2. So now I'm going to treat it just like the equations we did in part 1. So the first thing that I like to look at here is whenever I do the reciprocal functions, I flip to the reciprocal, so I change secant to cosine, and then I flip the other side. So remember, anything that doesn't have a denominator secretly has a denominator 1. If you divide by 1, it's just itself. So this can become cosine z equals 1/2. The reason I wanted to do this one is because what I see a lot is, see how this is x divided by 3. Sometimes people flip and they end up flipping that to 3 over x. But that's incorrect. That actually does not get affected at all. So that's why I would kind of make that replacement first, like make that substitution in there, then do your flip, and then we'll deal with the x divided by 3 once we get our angles. My reference is 60 degrees. Cosine is positive in 1 and 4. So that means I'm looking at z equals 60 degrees plus 360k. And I'm looking at 300 degrees plus 360k. change this back to x divided by 3. To get x alone, I'll multiply both sides by that 3. So I get x equals 60 times 3 is 180. 360 times 3 is 1080. 300 times 3 is 900 plus 1080 degrees K. And because it said for all values, I'm just going to box it in right here. If it said some kind of interval, then we would want to give answers within that interval, but we don't have to worry about that for this one. All right, so that's going to be it for that little subsection. Next, I want to talk about using identities. Okay, before we completely get into these sections, something I want to remind you of is in the very beginning of chapter 6, I went over a little bit of factoring. So I'm going to scroll up real quick. I'm going to go back to where we did that. All the way back up here. Oh, that's graphing. Came right after that. After this. Okay, here we go. I talked about factoring a little bit, and so we are going to do some factoring in these next couple examples. Some of them we will, some of them we won't. But something I just want to remind you of is that we have done factoring in an earlier video. If you need more assistance with factoring, you may need to watch like an algebra video just to help you out. So I just kind of want to let you know that before we get into these next couple examples. Alrighty, so I'm still going to need my little table and everything, so let me go ahead and drag that down with us. So my next kind of example here, I'll say this is example 2. So this little subsection is we're going to use some identities. Whenever you're using identities, I'm going to talk about like why we might want to use them. If ever you have like multiple trig functions, or if you ever have multiple, like maybe you have multiple trig functions, but maybe it's all sine, like it's all one the same trig function. But if there's like different stuff in the parentheses, you may need to use an identity right there to fix that. If you ever see some where it's like you've got sines and you've got cosines or anything like that, if you've got multiple different trig functions, that also might be one that you need to use identities. Now, there's different types of equations. You know, it's hard to kind of show you just one of everything, but those are some things to look for if you're thinking you might need to use an identity, especially the different like parentheses thing, because your whole goal is when you're doing any kind of solving equation, your goal is to get it to look like where it's just one trig function equal to some number. That's your whole goal. So let's look at a few of these. So for the first one, I'm going to do, I'm just going to say solve for x in the interval. We'll just say 0 to 2 pi. So we're just going to do like one rotation around the circle. So for our first one, we're going to see sine squared x plus sine 2x plus cosine squared x equals 0. Okay, there's a bunch of issues with this one. One, I've got a sine and I've got cosine in here. That's a problem. The other problem is that I have stuff with 2x and I have stuff with just x. That is a sure way to tell that you need to use identities. So if we look here, and sometimes it can be hard to identify which identity to use, but if I think about this and I see that I have that sine squared and that cosine squared, sine squared and cosine squared are an identity together. So the Pythagorean identity says sine squared plus cosine squared is equal to 1. So that means that these two pieces can go away and I can just replace it with a 1. So what I'll have now is I'll say sine 2x plus 1 equals 0. Now that I have one trig function with one set of parentheses, I can just work with what we have. So now it kind of looks like one of the problems we were already doing. So first I'm going to let this be z, because that's my preference. So I have sine z equals, if I move this 1 over, I have -1. Sine equals -1 down here at 3 pi over 2. So this is 3 pi over 2 plus 2 pi k. I need to replace back in that 2x. So 2x equals 3 pi over 2 plus 2 pi k. Divide out this 2. Remember that dividing by 2 is the same as multiplying by a half. So this is going to give me 3 pi over 4 plus pi k. If it had said for all values, we would just stop right there. But since it wants values between 0 and 2 pi, so one of my answers will be 3 pi over 4. And then we can see if I add pi over 4 to, pi to this, which would be 4 pi over 4, I get 7 pi over 4, which is still less than 2 pi. 2 pi would have been 8 pi over 4. 7 pi over 4 is still less than that. So we have two acceptable answers here. If you put this in degrees, that would have been fine for me. Like on a test in degrees, this would have been x equals, this is 135 degrees, and this is 315 degrees. Now the nice thing is you can always go plug these back in just to check your answer. I do think that takes up a little bit of time, so I'd really only do it if you have the time for it. But it's nice to do. Another using identities example. This one is sine, I don't know why it's in bold. Sometimes it just does that. Sine 2x minus sine x equals 0. So this one, I have two signs. That's great. But the issue is I have different parentheses. So when I look at this, there is an identity for sine 2x. There's something I can replace this with. So if you go back to your identity sheet, remember that is on our Canvas page. On, if you're watching this video and taking this class with me, of course. But it's the double angle identity, so it says sine 2x is equal to 2 sine x cosine x. Now you may be like, but that's going to change it, that's going to add me in a cosine. Don't I not want multiple trig functions? You'll see. You'll see what we do. I'm going to replace this. So I have, instead of sine 2x, I'm going to say 2 sine x cosine x minus sine x equals 0. Now we have to do some factoring. So right now I have two terms. Both of these terms have a sign in them. That means that I can factor a sign out to the front. So I can take a sign out to the front. If I take sine away from 2 sine x cosine x, I'm left with 2 cosine x. If I take this sign away from sine, I have a placeholder of 1. Now remember, when you factor, like if you have something like this, it says x minus 2, x plus 3 equals 0, you can set both of these parentheses equal to 0. Same thing if it said like x times x plus 3 equals 0, you'd have x equals 0 and x plus 3 equals 0. We're going to do the same thing here. We're going to have sine x equals 0 and 2 cosine x minus 1 equals 0. So what this has done is we've changed it to where we could factor, and then now we have each equation set up where we have one trig function and we'll be able to set it equal to a number. Sine x equaling 0, so that happens here and here, so that's going to be x equals 0 plus, that would be pi k. On the other side, I have cosine x equals 1/2. My reference is 60 in quadrant 1 and 4. Or I can write it as pi over 3 if I want to leave it in radians. So this would be 0 pi over 3 pi and 5 pi over 3 would be my answers. The 0 and the pi are coming from that sine x equals 0. The pi over 3 and 5 pi over 3 are coming from the cosine equals 1/2. In degrees, which I don't mind if you leave it in degrees, it would have been 0 degrees, 60 degrees, 180 degrees, and 300 degrees. I'll do one more of using identities before we do a like some quadratics and stuff. So part C, I want to do one with like tangent. So tangent 2x plus tangent squared x equals secant squared x minus 1. And there's different reasons that you might want to use identities. Sometimes it's like to cancel something out. I might bring up another one like in the review video if you guys need to see more of those. There's maybe some more I can come up with. Sometimes it's to cancel things out. Sometimes it's to be able to factor something. I mean, it's hard to say really. There's just so many ways you can use it. In this one, what should reach out to you is, okay, I've got a bunch of tangents here, and then I just have the secant thrown in. But you can notice that you have secant squared, and then you have a 1. So hopefully that reminds you of the Pythagorean identity. If not, it's all right. But there is an identity that includes tangent squared, secant squared, and a 1. So if you're seeing all 3 of those in a problem, you're probably looking at something with that identity. So that identity says tangent squared x plus 1 equals secant squared x. If I move this 1 over to the other side, I get that tangent squared x is equal to secant squared x minus 1. So that means this right here is just tangent squared x. So if I replace that, I have tangent 2x plus tangent squared x is equal to tangent squared x. If I subtract this tangent squared x over to the other side, it's just going to go away. So I'm left with just tangent 2x equals 0. And tangent equals 0, the same place as sine equals 0. It's here at 0 and here at pi. So this would be, you can replace it if you want, but I'll skip that step only for this one. But it would be 2x equals 0 plus pi k, divide by 2. I get 0 plus pi over 2k. You could box this in if it said for all values, but since earlier it said between 0 and 2 pi, I'll write out my answers, which would be 0, pi over 2, pi, and 3 pi over 2 are all going to work in this. To get these answers, just in case it's not clear, I'm adding the pi over 2 to each answer to see if I get another one. So like 0 plus pi over 2 is pi over 2. Add pi over 2 again, and I get pi. Add pi over 2 to pi, I get 3 pi over 2. Now, if I added it again, I'd be within 2 pi, and the interval had the 2 pi with a parentheses in the direction, so I don't want to add that in as another answer. 0 was enough. All right. So for our next little topic, we're going to do some quadratics. Let me see what time we're at in this video. Oh, 38 minutes. We're going good. Oh, is it going to crash? Sometimes it does that whenever I go back and forth during the video, it always like crashes it. Not sure why, but alrighty, let me go ahead and I'm going to bring my little table and everything back down with us. Alright, so next we're going to talk about quadratics. So that's like the next kind of subsection. So if you're like, you keep saying the word quadratic, I don't even know what a quadratic is. If that's how you're feeling, I will remind you. So a quadratic is when your highest power is squared. That's a quadratic. So in previous, in algebra and stuff, you may have seen something like this. This is the general form of a quadratic. It just means highest power is a squared. And so there's a lot of different types of problems you can see with quadratics. There's different ways to solve quadratics in algebra. So in algebra, the different ways are you've got square root property, where you can square root both sides. You've got factoring, And factoring can be a lot of things. It just depends on what it looks like. Sometimes you might factor a difference of squares. Sometimes it might be a trinomial where you have like an A, a B, and a C. You also have completing the square is possible. That one's not always ideal. It's only really nice in, you kind of have to have good numbers for that one to be nice to work with. And then you've got quadratic formula. Quadratic formula is nice because it works all the time. Although I could definitely show you some that require you to use quadratic formula and trigonometry at the same time, I'll let you know that I probably won't be doing any in this video. The reason is your textbook doesn't really get into those, and I think it's just because our class that we have, we try to structure it to not really need calculators. And so if you're needing to use quadratic formula, you're probably needing to use calculators. And so I try to make these problems where you don't need a calculator, so you get luck out a little bit on some of the harder problems that you could see with these. All right, so let's get into it. Let's do some examples. So for example 1, I'll just say solve for x, and we'll just say between 0 degrees and 360 degrees. I'll do degrees for these. I can do radians. I mean, whatever. So part A, I'm going to do sine squared x equals 1. And so you can kind of think about what you would do with this. Me personally, because I see that I just have a squared on one side and a number on the other, I would just square root both sides. And that would cancel out the squared on the left. Now be careful when you square root, you have plus or minus. So this would become sine x equals plus or minus 1. So this means that we want to find the angle that can make sine either a positive one or a negative one. We want to consider both. Well, positive 1 is up here at pi over 2. Negative 1 is down here at 3 pi over 2. So my answers here, I'd have pi over 2 plus 2 pi k, and I'd have 3 pi over 2 plus 2 pi k. If it said for all values, I'd box it in right now, but it only wants between 0 and 360, so I would do pi over 2 and 3 pi over 2. Now, of course, I did just do radians. The question asked for degrees, so it would be best to write this one in degrees, which would be 90 and 270. Hopefully that wasn't too bad. It was just, you just had to square root. Let's do another one. Part B, let's do cosine squared x equals 1/4. If I square root both sides here, be careful, this is plus or minus, you get cosine x equals plus or minus square root 1 over 4. So square root of 1 is 1. Square root of 4 is 2. So I have plus or minus 2. Well, my reference here is going to be, if I look at my table, 60 degrees. Cosine is positive in quadrants 1 and 4. It's negative in 2 and 3. So I'm pretty much just looking everywhere. I want all the angles that have a reference of 60. Any of them would work in this. So for my answers, I'll have 60 degrees for quadrant 1, 120 for quadrant 2, 240 for quadrant 3. To get those, I'm just either adding or subtracting 60 from 180. To get the quadrant 4, this is 0 or 360. Minus 60 is 300. So these are all my answers. If you had to leave it in radians, it would be pi over 3. Let's write that a little nicer. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 would be your answers in radians. Now, of course, these can get a little harder, mostly if they get into factoring. Let's do one that requires some factoring. This one's going to be part C. And we'll do tangent squared x equals tangent x. I like this one a lot because I always see the same mistakes on it. Most people, what they will do with this one is they'll divide both sides by tangent, and they'll say, okay, I'm going to divide by tangent x, and that's going to give me tangent x equals 1. You'll get partial credit. Like, you'll get like part of your answers. You're going to get some of the correct answers, but you actually miss out on quite a bit of answers doing it this way. And it's because you really don't want to divide by a whole function like that, because you just miss out on some answers. So it's very similar to if you had something like x squared equals, let's say x. The thing is if you divide both sides by x, you get x equals 1. And it is true, 1 squared does equal 1. So that's true if you plug that in. The problem is there's another answer here that you're missing out on, and it's 0. If you plug in 0 squared equals 0, that also works, but you missed out on that answer. So what happens here, what we should do, is we should say x squared minus x equals 0, and then you can factor out an x, and you're left with x minus 1, and then you can set both pieces equal to 0. That's what we should do. And so what my advice to you is, anytime you deal with a quadratic, you should get all of your stuff with your variable on one side. Every time. Even if you're going to use square root property, you can think of that method. If you are going to if you might need to be factoring or something like that, you're going to need to move everything to one side. So if you see a squared, move everything with the variable onto one side. Now, we might need to move absolutely everything to one side, but it really depends on the question. I'll show you some later that we have to do that. So right now, I'm going to move everything over. So I have tangent squared x minus tangent x equals 0. Now I have two terms that both have tangent, which means I can pull a tangent out to the front, just like I did here with this x. And I'm left with tangent x minus 1, and it still equals 0. Then I can make my two equations, so tangent x equals 0 and tangent x minus 1 equals 0. Now I'll go ahead and get my angles. Tangent x equals 0, x would equal 0 plus pi k, or 180k. Here, I'll do 180 for this one. tangent x equals 1. Be careful, my reference here is 45 degrees. Tangent is positive in 1 and 3. So this would be x equals 45 degrees plus 180 degrees k. Remember, for tangent, you don't add 2 pi, you just add pi always. And you don't have to write both answers, you can just write the 1, because if you add 180, you would get the quadrant 3 answer, so you don't have to write them both. If the question said for all values, we would box this in right here and we'd be done. Because it wants between 0 and 360, I'm going to list out my appropriate answers. So I get 0 degrees, 45 degrees, 180 degrees, and 225 degrees. Just in case you want to see it in radians, it would be 0, pi over 4, pi, and 5 pi over 4. So that's one factoring example. The other factoring example we will do is a trinomial. And now these can look different by not even changing very much. For instance, I could turn this question, I can make this a cosine, sine, cosecant, secant. I can do a lot of things to it. I can make this where, let's say I put a negative inside of that parentheses. Then you've got to use even odd identities to pull that negative out to the front. And then you would add it to the other side. So I can change these questions a good bit by not even really doing that much to change it. I can make this a sine squared x equals sine x. It's still the same process. It would have just been sine instead. Something you should always remember if you're ever looking for more practice with these is you can always change the questions just a little bit and try them out, and you can plug them into something to then see if you get your answer correct, like an online calculator. Now, sometimes making stuff up can be difficult with trig because, the references and stuff have to be correct. So sometimes it might work, sometimes it might not. It just depends. With these, it'd be fine. Let's do a factoring a trinomial example. So the first one that I'm going to do is, what part is this? Part D. I'm going to do 2 cosine squared x plus 3 cosine x plus 1 equals 0. This is a trinomial factoring example. What we mean by that, a trinomial, is that there are 3 terms in the polynomial. So we have a cosine squared, we have a cosine, and then we have just a number. So it looks a lot like that ax squared plus bx plus c type. Now, if you wanted to here, you could plug into the quadratic formula and get your x values. However, what you'll have to be careful of is when you get that quote-unquote x value, it's really cosine equaling that x value. So you'd have to be a little careful. You'd still have to find the angle. I can show you if you'd like to see, but, well, you can't tell me if you want to see, but maybe I'll show you just in case. I'll explain it at least. When we're factoring something like this, something that could help you is if you would like to replace the cosine x with another letter. Sometimes that can help a little bit, just so it doesn't look as spooky. So I'm going to let cosine x be some letter. I'm just going to pick, let's do, I did Z earlier. Let's just do a B. We're just going to do B. It doesn't matter. But this has a B in it, so I don't want that to confuse you. So let me do, maybe not B. let's do z again. That's fine. We'll just do z. So then I would have 2z squared plus 3z plus 1 equals 0. So when you do trinomial factoring, you have your two sets of parentheses. Your two numbers in the front here need to multiply together to equal 2z squared. To equal 2, the only two numbers that can do that are 2 and 1. So this is going to be 2z and z. Your two numbers in the back here need to multiply to positive 1. There's only two numbers that can multiply to a 1, and it's 1 and 1. Because this is a plus, my two signs need to be the same. Because this is a plus, they're both going to be plus. So I get 2z plus 1 equals 0, and I have z plus 1 equals 0. But be careful here. It's not just z. We got to plug our cosine back in. So I get 2 cosine x equals 1/2. Oh, sorry, y'all. I'm working ahead. Positive 1 equals 0. And I have cosine x minus 1 equals 0. Plus 1, sorry. Solve these for cosine x. I get cosine x equals -1/2, and cosine x equals -1. What I was trying to say earlier is if you had used quadratic formula on this, so if you had done x equals -b plus or minus square root b squared minus 4ac divided by 2a. If you use quadratic formula, the x values that you get here are going to be -1/2 and -1. So you still need to remember to do cosine equal those. So if you use quadratic formula, you should get here, and then from here it's the same process as what I'm going to show you. Cosine x equals -1/2. This is just like our beginning of our section. So my reference here is going to be 60 degrees. Cosine is negative in 2 and 3. So I get x equals 60 degrees. And quadrant 3. Oh, be careful, be careful. I did something wrong there. 60 degrees would be quadrant 1. I need the reference of 60, but quadrant 2. So that would be 120 and 240. Now watch it. Cosine x equals -1. That happens over here at pi, which would be 180 degrees. So these are all my answers. So just for purposes of writing neatly, this would be 180 from this answer. So my final answer, I would just list all of my angles out. If you don't put them in order, that's not a big deal. I just do it. In radians, this would have been, let's see, that'd be pi over 3. This would be 3 pi over 3. So that would be 2 pi over 3, pi, and 4 pi over 3. And so again, I can change this one just a little bit by making it like a sine instead of cosine. The factoring ones, there's really only so many that I can do. And it's like I said earlier, I try to make these where you don't need a calculator. So you have all the references and everything. If any of these were weird, like where it didn't have a reference of 30, 45, or 60, that's when we'd have to use those general forms that I talked about in the last video. And I'll just do one more of kind of this factoring example. So we're on part E here. This one, let's do I'll do a sine one. We'll do 2 sine squared x minus sine x, let's say equals positive 1. Yeah. In this one, because you have that squared, you have a function without the squared, and then you have a number by itself, this is another trinomial example. So we need to move everything to one side. So what some people will try to do with this is they'll try to factor out the sign, and they'll do something like this. This is bad, but I'm going to show you. They'll do like sine x, and then they'll do like 2 sine x minus 1 equals 1. And so then they'll say sine x equals 1, and then 2 sine x minus 1 equals 1. Okay, you cannot do like this method of setting parentheses equal to the other side unless that other side is 0. So that's the first thing, is when you're doing something like that, and you're splitting those equations up, it has to be a 0. And it's because the actual rule is a times b equals 0 if and only if a equals 0 or b equals 0, and vice versa. So if and only ifs can go each way. So what's happening here is when you're saying two things are equal to 0 if they're multiplied, that means either the a or the b has to be 0 for that to happen, right? Because anything multiplied by 0 is 0. So that's why we need it equal to 0. Otherwise, it doesn't work. You can't do it. Because to be equal to 1, I mean, that doesn't tell me anything. All right, so I'm going to move that to 1 over sine squared minus sine x minus 1 equals 0. Again, you're welcome to let that trig function be something else temporarily. I'm not going to worry about it on just this one. So I'm just going to go straight into factoring. So I have trinomials. So I have 2 sine x and sine x. I have 1 and 1. But here's the tricky part. I don't know which one to make positive and which one to make negative, because this negative right here means they have to be different sides, different signs. This minus right here means I want the bigger number to end up as the negative when I FOIL it out. So if I kind of think ahead a little bit, I'm just going to kind of check with you a little. Let's say I put the minus right here and the plus here. What will happen here when you FOIL it back out is when you get those middle terms, you're going to have 2 sine x minus sine x. That's not going to give me a negative sine x. What I want to happen is I want this to be plus and this minus, so that when I FOIL it out, I get negative 2 sine x plus sine x. So you kind of have to think ahead just a little bit to figure out where you want that plus or that minus. If this middle sign right here had been a plus, then we would have had it the first way I wrote it. All right, so now I'll set each equation equal to 0. Oh, I missed my x right here. Don't do that. Bad notation. So then I have sine x equals negative 1/2. Sine x equals 1. Sine x equaling negative 1/2. My reference here is 30 degrees. And sine is negative in 3 and 4. So I'm going to have my quadrant 3 answer would be 210. My quadrant 4 answer would be 330. And just a little note here, if you had this as solve for all values, it would have been plus 2 pi k, and then we would have had 330 plus 2 pi k, and then the other side, sine equals 1 at 90 degrees plus 2 pi k, or I really should do 360k since I'm in degrees. There we go. That looks a little nicer. So if it had said for all values, we would just box this in and we'd be done. But it wants in the interval, so we're just going to write them all out. So it'd be 90, 210, and 330. In radians, that would have been pi over 2. This would be pi over 6, so that would be 7 pi over 6. 11 pi over 6 minus pi over 6 would be, oh, I said the answer, 12 pi over 6 minus pi over 6 gives me 11 pi over 6. So that would be the answers in radians. This is it for our solving equations sections. This is it for 6.5, part 2. So as always, I hope you have a wonderful day. And if you're in my class, please email me if you have any questions, okay? I will see you on the next video. Bye-bye.